essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation.
What existed before the Big Bang? This question has challenged scientists for decades, but recent discoveries have revealed something extraordinary about our universe's origins. When we talk about the Big Bang, we must be precise.
It was there, in a sense, cold and empty, and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever. And it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, stretch, stretch. And then it slows down and stops in little patches. And each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse.
The Big Bang represents the moment when our universe was incredibly hot and dense. We know this happened because we can observe it. We can literally see the evidence in cosmic background radiation. But our best theories suggest there was something before that moment, something called cosmic inflation. Picture this. Before the hot, dense state we call the Big Bang, the universe existed in a completely different form. It was cold, empty, and expanding at an unimaginable rate. This expansion eventually slowed and stopped. When it did, all that energy was released into space, heating it up and creating all the particles from which we are made. That moment is what we call the Big Bang. The theory of inflation has a remarkable extension called eternal inflation. This suggests that inflation continues forever across the cosmos, stopping only in small patches of space-time. Imagine the fabric of the universe stretching endlessly, then suddenly slowing down in tiny regions. Each region becomes its own Big Bang, its own universe. Our cosmos is just one patch in this infinite tapestry, one universe among countless others in what scientists call the inflationary multiverse. This raises a profound question. Can true nothingness actually exist? In our vast cosmos, absolute emptiness appears more theoretical than real. Even if we could remove all energy from the universe, it wouldn't be truly empty. Currently, space teems with matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Here's something that confuses even physicists. Even without energy, the universe continues to create new forms of energy. The cosmos doesn't understand our concept of complete emptiness. If we removed all energy, we might expect the universe to reach absolute zero with no particles. But that's not what happens. Even in an apparently empty universe, its expansion would still produce radiation. Something always persists. Even if we remove particles, antiparticles, photons, and energy, empty space itself remains. And this space isn't truly empty. Even in the most isolated region of space, quantum fields endure. The fundamental constants and laws of physics persist. There is an inherent energy value in that space, what physicists call zero-point energy. This represents the closest approximation to nothingness within our universe. While you might imagine an even emptier state, it lacks physical reality. No experiment can replicate such a condition. By following scientific principles, we must acknowledge that something always exists, because true nothingness cannot coexist with our universe. Currently, our universe is far from empty. It's filled with stars, gas, dust, galaxies, and radiation from both starlight and the remnants of the Big Bang itself. The fabric of space-time is expanding. This means that if you place 2 points far apart in space, the distance between them and the time light takes to travel between them both increase over time. The universe isn't just getting bigger, it's also getting colder. As light stretches to longer wavelengths, it moves toward lower energies. The universe was hotter in the past and will become even colder in the future. If you could somehow remove everything, all matter, all radiation, every bit of energy, what would remain? You'd still have empty space itself, still expanding, still governed by physics, still influenced by quantum fields. This is the closest physical approximation to true nothingness, yet it still follows specific physical principles. There was a period in our universe's history when something other than matter and radiation dominated everything. During cosmic inflation, prior to the Hot Big Bang, our universe underwent extremely rapid expansion. Instead of being dominated by matter and radiation, the cosmos was controlled by the energy field of inflation, similar to today's dark energy, but far more powerful and expanding at an incomprehensibly faster rate. This inflationary period may be the key to understanding not just what came before the Big Bang, but why something has always existed instead of nothing at all. The universe has been expanding, creating and evolving for far longer than we ever imagined. It may continue to do so forever, spawning infinite universes in an endless cosmic dance that began long before our own Big Bang. In the end, the question isn't really what existed before the Big Bang. The question is, what if the Big Bang was never really the beginning at all?